So there are three main types of heat flow. Okay. I think one of the major issues that people have is determining the system versus surroundings. So the system is what we study. In the case of your calorimetry lab, that would be the metal. Our surroundings would be everything else. So the heat of the metal had to go into the surroundings, into the water. Okay. The internal energy of the system, okay, this is what we're studying, is the sum of all the kinetic and potential energies of all the components of the system. So we define what the system is. What are we looking at? That is our system. We can't measure an absolute energy. We can't take a snapshot, here's our energy. But we can measure the change in this internal energy. And so we represent energy, as we've seen before, in this case, as just delta E. Sometimes when you go into upper level chemistry, or if you look on the internet for more about internal energy, you might see it represented as delta U. That's a different notation. It means the same thing. What is the internal energy? So when we're measuring the change in internal energy, we have to have an initial energy and a final energy. The change in energy is represented by this delta symbol. So delta means change. So this is the difference in the final energy and the initial energy. So when we look at the internal energy of a system, we know from all the previous slides, and from the first law of thermodynamics, that energy cannot be created nor destroyed. So that means it has to come from somewhere. It can be transferred, converted. We also know the energy of a system plus the surrounding is constant. So we know that if energy cannot be created nor destroyed, that means the total energy has to be the sum of the system and surrounding. And it does not change. Any energy transferred from the system must be transferred to the surroundings, or vice versa. All this is saying is that your energy has to be kept constant. Okay, your total energy of the universe, of the whole entire universe, has to remain constant. If you're just looking and narrowing it down to a systems and surroundings, so in your calorimetry experiment, we're not looking at the whole universe, are we? We're looking at just a subset. And that subset was the calorimeter and the water and the metal and things like that. So that energy of our new system and surrounding has to be constant. So the energy is an exchange, and we can exchange it in two different ways. It exchanges in work, or it's exchanged in heat. Okay. So another equation that we've seen is the delta E is equal to the heat represented by Q and the work represented by W. Please do not ask me why is heat Q? Basically, for the heck of it. There's way too many H's and too many energies, and we chose Q. I think it's some sort of, I think it came from some language, maybe Latin. I can't remember. But the total internal energy, is the sum of the heat and the work. And we can learn a lot about this energy transfer just by looking at signs. So if heat is greater than 0, so if it's a positive number, okay, that means heat is going into the system. If work is greater than 0, so if work is positive, that means it's going into the system. Where did it come from? It came from the surroundings. So that means the surroundings is giving and putting in energy into the system. That means the total energy has to be greater than 0. If the system is losing energy into the surroundings, then it becomes negative. So here's some sign conventions. This nice little chart to look at how energy is transferred and what does it mean. So If Q is greater than 0, that means heat is transferred from the surroundings into the system. If it's negative, that means the system is losing heat and it goes into the surroundings. Same way, we can define work. If work is greater than 0, that means work is being done by the surroundings. So work is being done on the system by what? By the surroundings. If W is negative, that means the system is doing work, and that work is done on the surroundings. Now, we can have different combinations of whether Q is positive or W is positive. It doesn't always have to be the same. So you can have both of them being positive, you can have both of them being negative, but you can also have one being positive and one being negative. And so that's going to change your delta E. And you can plug in some values and see how this changes, but the sign of E, in these two cases at least, will depend on how big those numbers are for Q and for W. So some other misconceptions when we talk about energy, and we're talking about heat in a second, is definition. So we've talked, I briefly mentioned endothermic and exothermic processes. Okay, you might hear, or I know a lot of you people look on the internet for help and things like that, and that's okay. But what you need to pay attention to is these definitions. There's endothermic and endergonic. Those have two different meanings. So endergonic, you might hear, just refers to any type of energy. Endothermic specifically means heat. So it's a transfer of heat. Just like thermodynamics is the study of heat, transfer of heat. So we have endothermic, where the system absorbs heat from the surroundings. So this should feel cold. And if you guys remember from last week, that means delta E has to be greater than 0. Exothermic, the system transfers heat into the surroundings and it feels hot. So a cold pack, how it works is it has, depending on what you have, it has different chemical reactions. You break that open, break little packets open, and these chemicals interact. And for a cold pack, these are an endothermic process, which means it takes heat from the surroundings. And you remember our definition of heat, it always goes from hot to cold. It's not going from cold to hot. So we describe that as an endothermic process, and it feels cold. It's taking away from the system. Sorry, it's taking away from the surroundings. And so the surroundings are getting colder, and that is what you feel. Exothermic is the system transferring heat to the surroundings. So for a hot pack, same kind of deal. You break it open, chemical reaction occurs, but these are exothermic reactions. So when you form bonds, it releases energy, and it feels hot. And the delta E of that is going to be less than 0, negative. So you remember from chapter 7 all the way back there that we prefer energy at a low state. So the lower the value, the more stable it is. So we describe these systems as exothermic and endothermic. Okay. If we're just talking about energy in general, so work or heat, we call it endergonic or exergonic. And will this show up? Maybe. It will specifically show up if you are going to take your, continue on with your chemistry courses and you go to take physical chemistry and things like that. For this class, we're really going to focus mostly on heat, so using endothermic or exothermic is going to be more proper. And when we talk about heat in the sense of, well, why is it changing? There we go. Of measuring heat flow. Where did it come from? Where did it go? So if we look at this, this should look familiar to you, right? This is from your lab. So we can use calorimetry to measure the transfer of heat or the heat flow in a reaction. The reaction that is occurring is called the system. The calorimeter is the surroundings. So here's your little coffee cups, if you guys remember. This one's a little bit different, but the artwork's kind of weird. But you have your system in here. Okay. So it's some reaction in solution. In our case, we had metal and water. And you have a nice insulated calorimeter. Ours was not that great, was it? It was just a couple of coffee cups and a piece of cardboard. So it wasn't perfectly insulated, but it was pretty good. Good enough to make the assumption that we have a fully isolated system. So what happens here is that the Q of the reaction, so the heat of the reaction, has to equal negative calorimeter. Now the way we did it was a bit different. So we didn't just say our calorimeter, we also included that of the water. So the heat of the metal, if you remember that, is equal to the negative heat of the water. So ours was a bit different, but the same sense, where heat of the surroundings and the heat of the reactions are the same. Okay, it's the same value, just different signs. So something's gained heat, something lost heat. So in this case, what lost heat? Whatever has a negative sign, in this case, the calorimeter. And in calorimetry, what you had to do in the lab is to measure the specific heat. So the specific heat is the amount of heat required to raise the temperature of 1 gram of an object by 1 degree Celsius. So you can see here, we're looking at the specific heat. There's other heat capacities that you can consider. So in general, a heat capacity, not just a specific heat capacity, but heat capacity is the amount of energy required to raise the temperature of an object by 1 degree Kelvin, or 1 Kelvin, I should say. There's no degree. So how much heat is required to basically raise the temperature? So if you think about a pot of boiling water, what's going to heat up faster? If you have a metal pot and water, what's going to heat up faster? What requires more energy to heat up? So in this case, the metal pot will heat up faster. Okay, it required less energy to raise the temperature than water. So the specific heat of water is 4.184 joules over grams Celsius. The specific heat of metal is about much lower. So depending on your metal, if you guys remember from your lab, it ranges from about 0.1 to 0.7 joules per gram Celsius. And so we have seen this in lab using specific heat of water, the mass of water, and the change to calculate the heat of water, which can then be related to the heat of the metal. Oh, and one more heat capacity. This is a molar, and this is just talking about in a moles of the substance rather than just a gram. So they are. This one would use moles. This one would have grams. This one doesn't have anything about weight. Okay. And here are some specific heats you can see as you go from some metals that are very low to liquids. You can see that it takes more energy into a system to raise 1 gram of your substance 1 degree Celsius.